So today we're going to be applying properties of similar triangles. Applying properties of similar triangles. And the first theorem in this section says that if a line is parallel to the side of a triangle, and intersects two sides, then it divides those sides proportionally. A picture of it would look something like a triangle. And then we'll take this red line and we'll intersect two sides of the triangle and we'll make it parallel to this side. The large triangle, or the triangle around the outside, has vertices ABC, and the line that's parallel to BE intersects the triangle at EF. I'm sorry, this is down here. This is a C. And this is EF. The theorem says that in this situation, segment AE over segment EB is going to be equal to, or proportional, it's going to be equal to AF over FC. Now, keep in mind when you're dealing with proportions, if this is true, remember in a proportion, cross products are congruent to each other, right? It means that you can switch EB and AF, or you could switch AE and FC, or you can switch them both. So there's other combinations that you can use in that proportion that would still be true. And here's the example they give you in this, over on the next page, on the top of page 496. They tell you something like this segment right here, A to E is 4, and E to B is 9. A to F is 10. And they ask you to find FC. So find FC. So you just write a proportion. So the rule says that 4 over 9 is going to be equal to 10 over whatever F to C is. You can make it a variable if you want, or you can just call it FC. And then when you're solving for a missing term or variable in a proportion, you crisscross multiply. So in this case, you would take 4 times FC and set it equal to 9 times 10, which is 90. So, yep, divide by 4. So this cancels, and FC is going to be equal to 22.5. The converse to that theorem, which is in the middle of page 496, says if a line divides two sides of a triangle proportionally, then it is parallel to the third side. If a line divides two sides of a triangle proportionally, then it is parallel to the third side. So you may see, this is the type of question you'll see. If you're given this diagram, there's two ways you'll see this question. You can be given this diagram, and you could be asked, is KL parallel to MN? Is KL parallel to MN? Well, does MN divide the two sides of this triangle proportionally? Okay? Look at the proportion 42 over 21. Is 42 over 21 equal to 30 over 15? Yeah, a lot of you can just see that 21 is half of 42. 15 is half of 30. So MN divides these two sides proportionally, so it's parallel, right? Now, if this happens, if this 15 gets changed to a 16, now, are they parallel?
No.
Now they're not parallel because the proportion, or because the segments wouldn't be proportional. All right, 21 is half of 42, but 16 is not half of 30. All right? The third way you'll see the question is you could be asked to find NL so that M to N is parallel to K to L. So in order for M to N to be parallel to K to L, you would have to solve for this piece in this proportion. Agreed? So again, you would just write a proportion and solve for N to L. Does that make sense? So those are the three ways you may see questions related to that rule. You're either going to be asked if the lines are parallel, or you're going to be asked to find a segment length so that the segments are parallel. And your third rule today is on the bottom of page 496. And it says if three or more parallel lines intersect two transversals. And they divide the transversals proportionally. So a picture of that, if three or more parallel lines, so three parallel lines, intersect two transversals, then they divide the transversals proportionally. So if your points of intersection are AB, CD, and EF, it's the same concept of the theorem we just covered, except they don't show the transversals intersecting. They don't show them forming a triangle, do they? But if you extended these two vertical-ish lines, they would intersect up here somewhere, wouldn't they? And then if you chop the bottom off and you stopped them at this bottom horizontal line, it would just form a triangle. Okay? So it's the same concept that you just covered. It just looks a little bit different in the picture. So in this case, AC over CE, what would AC over CE would be equal to what? Very good. BD over DF.
So you just pick any letters and any word?
No. No. You have to stay consistent in the order that you pick your letters. Okay? So here's what I mean. If you started off with, I'm gonna call AC left top. If we go left top over left bottom, on the right hand proportion we have to go right top over right bottom. Okay?
I get that. So, but I'm saying like for the first half, I couldn't do AB and CD.
No, we're not talking about these segment lengths. All right, we're talking about the segments created by the transversals. All right, and now keep in mind what this says: if three or more parallel lines, because here's what you could see. You could see this extended to here and here, right? And wouldn't everything just continue to be true? I mean, if you keep adding parallel lines, all of the segments will continue to be proportional to each other. Okay? Does that make sense? I hope. No response? If this is G, H, I, J, K, and L. All right? Now, AC over IK. AC over IK, what's it going to be equal to? BD over JL. Very good. All right, you see it? And any and all corresponding combinations. All right? If we went GI over CE. GI over CE, what's that going to be equal to?
HJ over DF.
HJ over DF. And remember that you can switch these two. You can switch these two, right? Be aware of that. Look at theorem 744 on page 497. An angle bisector of a triangle. Divides the opposite side. Into two segments. Whose lengths are proportional to the lengths of the other two sides. So a picture could look like triangle ABC has an angle bisector AD. And it's an angle bisector because AD splits angle A into two congruent angles. The theorem says that BD over DC is equal to AB over AC. Now remember, it's a proportion, and you can switch these two, right? You have flexibility within a proportion. I think this rule is way easier to remember as an angle sector, an angle bisector in a triangle splits. Here's the proportion I think is way easier to remember. This piece over this piece is equal to this piece over that piece. See how the angle bisector created two segments? That the segment it created over the side next to it is equal to the segment it created on the right or bottom over the side next to it. That picture is easier for me to remember. That picture is easier for me to remember than, you know, this piece over this piece equals this piece over this piece. The first way is way easier for me. So, whatever you want to do. And here's what you may see as far as the question goes, that this piece right here, A to B, is equal to 10. And R to V is equal to x plus 2. D to C is 2x plus 1. S to T is 14. No, A to C. Yeah, I'm looking at the wrong letters. So, you could be asked to solve for x and then find B to D. You could be asked to solve for x and find D to C. You could ask to You could be asked to just find x, or you could be asked to find x and side BC. So all of those combinations of questions. So I think it's easier to put x plus 2 over 10 and make it equal to 2x plus 1 over 14. When you crisscross multiply now, you're going to end up doing the distributive property, so you're going to have 14 times x plus 2, and it's going to be equal to 10 times 2x plus 1. Distribute, so 14x plus 28 is equal to 20x plus 10. Subtract 14x from each side. $28 equals 6x plus 10. Subtract 10. So 18 equals 6x. Divide by 6. 3 is equal to x. If you know that x is equal to 3, you could substitute it and find each of those segments or the entire bottom of that triangle. Yes, sir?
So we were trying to find x in that problem?
In that problem, it actually said find
Oh, I see,
B to
yeah.
D and D to C. Yeah, I changed the letters, that's all. So if x is equal to 3, then B to D is equal to, B to D is equal to 5. 2 times 3 is 6, plus 1 is 7. The whole segment would be equal to 12. Anybody have any questions? How about a little bit of practice for you today on page 499? Problems 8 through 20. And please remember to check headline for homework.